this lecture, we're going to go ahead and solve exponential equations. Solving exponential equations. There should be an S on that. Without logarithms. So we have not introduced logarithms yet. So don't worry about that word. I just want to let you know that we're going to focus in this lecture on solving exponential equations that don't require that type of object. Anyway, there are a few prerequisites here. You need to know everything about exponents, like laws of exponents, stuff like that. You also need to know how to graph exponential functions and how to solve equations using the method that I've been teaching this entire time. Solving equations using either one of two methods. Either if you have one version of your variable, then you untie the knot. If you have two versions or more of your variable, then you have to resort to special techniques. Believe it or not, this should be the very first time that you've seen an equation in this form. You've seen a lot of equations with stuff like 3x plus 7 is equal to 81, or 3x squared plus 7x plus 1 is equal to 81, or 3 times the square root of x plus 7 is equal to 81. All of these you should be able to easily solve or find a way to solve them. But this right here, you don't know how to solve it. The reason why is, well, ask yourself how you would solve this first one. It has one variable within the entire equation, so you can untie the knot. In other words, you rely upon undoing what's happening to x. So let's see, you would undo a multiplication by 3, so that involves division. I could do that. And you have to undo an addition by 7. That involves a subtraction. I could do that. So I could easily solve this equation. I'm going to skip the second one for a moment and go down to the third one down here. The third equation also has only one version of a variable, which means I can untie the knot. You just ask yourself again, what's happening to x? Well, they add 7, so I'll do the inverse of that, which is subtract 7. They take the square root of both sides, or at least the square root of x plus 7. I will do the inverse of the square root, which is squaring both sides. They multiply that by 3. I'll do the inverse of multiplication by 3, which is division by 3. This middle case here, this is a special scenario. So you have 3x squared plus 7x, and then plus some number equals some number. These two terms cannot combine, so you have to resort to special techniques. The special techniques here would involve moving everything to one side, in other words, subtracting 81 from both sides, and then either factoring or using a quadratic formula. So this requires a special technique. But these other two, the first and the third, are very straightforward. Now, going along those lines, this should also be very straightforward since you only have one version of your variable. The problem is we don't know how to undo one thing here. Watch, if I do what I normally do, which is ask you what happened to x, we start with focusing on x itself. So zoom in, just kind of look at x and say, what's the first thing that happened to it? Well, the first thing that happened to it is it got multiplied by 2. And the second thing that happened to it after it got multiplied by 2 is somebody added 7 to it. Both of those I can undo. I can divide by 2 and subtract 7. I can undo those. But the third thing that happened to this picture 2x plus 7 is it got raised. It is the exponent with base 3. So it got raised. It is now in this type of structure, and I have no idea how to undo that. You can't normally, so I'm going to cross that out. Normally, if it was like x to the third, I can undo that by taking the cubed root. See, those powers undo each other. But you have 3 to the 2x plus 7, and I would be totally confused if I took the 2x plus 7th root. Even though they would cancel, I still don't know what the 2x plus 7th root is. So, very bad idea. So right now I have no idea how to undo, or basically unlock, an exponent. I can't unlock a variable from an exponent yet. So my only choice is to hopefully write this 81 as a similar number, or as exactly the same number, but just a different representation. What I'm looking for is to use the following theorem. If you have a base b, that's supposed to be a b, I'm kind of butchered it, b to the nth power, and it equals that same base to the nth power, then you know those two powers have to be the same. M has to equal n. So I'd like to rewrite this equation to where both sides are just exponential expressions with base 3. Well, this 81 can be rewritten as 3 to the 4th power. So let me go ahead and do that. This implies the left-hand side I'm going to leave as 3 raised to the 2x plus 7 power. The right-hand side, that's 3 raised to the 4th power. And now since they have the same base, using this theorem where the bases are the same, then their exponents must be equal. So I'll go ahead and set the exponents equal here. Let's see, 2x plus 7 must therefore equal 4. And now this I can easily solve, right? Subtract 7, divide by 2, and we get this. X is a negative 3/2. That's how you solve all these exponential style problems where if you don't know what a logarithm is, that's how it's done. Now obviously there's going to be a point, I'll write this in red because this is not for our discussion right now, but there's going to be a point where you have like something like 3 to the x is equal to 17. And you cannot write 17 easily as 3 to a power. It's not very easy to do. So this you can't do using this method. This requires something called a logarithm. So I'm just gonna skip out on that right now because I'll dedicate an entire series of lectures to logarithms. Now, even though we don't have the technology of a logarithm, we still can solve a lot of applications that involve exponential functions. Let's take a look at this one. The number of people who hear of a campaign increases by a factor of 8 every 4 days. So that's the important part here, is that that's kind of their way of telling us a growth factor. So that's why you need to know everything about exponential functions prior to this lecture. If 100 people know of the campaign on the first day, write a function giving the number of people knowing about the campaign after t days. So let's start there. One thing we do know is that this 100 people that initially know, that will be our p naught. And in fact, maybe I should write down the standard form, or the form of the exponential function I'm going to use. I'll use p of t is equal to p naught b to the t. That's the exponential function format there. And p naught is just our initial value, our initial number of people. In reality, this is going to be, actually I'll write it up over here. This will be 100 times b to the t power. And now all I need to know is what is b? Well, they tell me that it increases by a factor of 8. In other words, it gets multiplied by a factor of 8 every 4 days. From our previous work with all the function notations and building exponential functions from word problems, we know that means that we have something like 8 in here, because it's every single group of days it gets multiplied by 8, and that happens every 4 days. So increase by a factor of 8 every 4 days. So that's our function. And now that was actually part A. So let me just rewrite that next to part A there. That we have p of t. So just in case I need to erase this, I don't think I will have to, equals 100 times 8 to the t over 4 power. Now graph your function by hand. That's going to be very difficult to do, but we'll give it a whirl here. So I draw some axes in here, and I'm going to go ahead and rewrite this in a graphing format. In other words, a form that's easier for me to graph with. That's like 100 times 8 to the 1/4 all being raised to the t. Remember, powers to powers multiply. And then I can use a calculator to figure out what 8 to the 1/4 is, because that's not going to be a nice number, I'll tell you that. So 8 raised to the 1/4 power. I'll get 1.68 roughly. And the reason why I like this format is just because this is how applications are generally handed to you anyways. They give you some nastiness. There's a lot of things you can take away from this. First of all, this is our initial value. That means at time 0, we are at a height of 100 on the vertical axis. So at time 0, the 100 people know of the campaign. And then from that point forward, it's being multiplied by powers of 1.68. So it's growing. I'll go ahead and just show how it might grow. It might grow something like this. Who knows? By the way, technically, if it's an exponential function, it should go this way. But the fact is, this is a real application, so we generally start graphing today, and we don't concern ourselves with the past. Now, a really cool interpretation of this number is that this means every day that goes by, the number of people that know increases by 68%. And I'm a big fan of that interpretation. So that's just a great thing to know, that when you have something like 1 point number, then you know that that's the percentage increase that's happening. Now, I would like to graph another point, so you could choose a value for t. Now, like I said, I wanted to kind of write this form out here just so we can get an idea of what the graph looks like. But in reality, I'm probably just going to choose t equals 4. If I choose t equals 4 in the original function without all my manipulation with a calculator, I get this. 100 times 8 to the 4/4 power, or in other words, just 100 times 8, which is 800. So that means at time 4, so maybe let's say this is 1, 2, 3, 4. So day 4, 800 people know. Now, of course, my graph is not to scale. This should actually be up a little bit higher, but I'm okay with that. 4, 800. Good exponential growth on that. Now, the part C of this problem is a really interesting part. It says, how many days should the campaign go on to reach an audience of 51,200 people? Remember, our function is this. The number of people who know is equal to 100 times 8 raised to the t/4, where t is the number of days that have gone on. We want to know when that number of people is going to be 51,200. In other words, we're going to let p equal 51,200. So let's go ahead and do that. 51,200 must equal 100 times 8 raised to the t/4. And you might think, I can't do this because there's just no way I don't know how to do this. Well, divide both sides by 100 first. Start easy. Start with just these simplifications. I can't talk today, or any day really. 100 over 100 is 1, and of course 51,200 over 100 is just 512. So let me go ahead and write that in. We get 512 is equal to 8 raised to the t/4. Now, geez, I would really love it if 512 was a power of 8. That'd be awesome. If it's not, then I have to resort to powers of, well, something that I can write 8 in terms of. If you grab a calculator and you start looking for powers of 8, you'll find out that 8 to the 3rd power is going to be 512. So this is actually equal to 8 to the 3rd power. Now, in a way, this problem's set up a little bit easier than I would like, because honestly, it'd be nicer if these two weren't so beautiful. It'd be nicer if we had to basically do a prime factorization on both. You can still do that. I could have said, listen, 8 is the same thing as 2 cubed. I could have done that. And on the left-hand side, 512 is the same thing as 2 to the 9th. And now, I would rewrite that as 2 to the 9th is equal to, remember powers to powers multiply, so that's going to be 2 to the 3/4 power, 3t over 4 power, sorry. So therefore, the powers, since the bases are equal, the powers must be equal, so 9 must equal 3t over 4. Multiply both sides by 4, divide both sides by 3, and you'll get that t is equal to 12. And just because in this case it happened to work out, since we can write 512 as a power of 8, you could have done it that way. You could have said, well, all right, that means the powers are equal, so 3 must equal t over 4. Multiply both sides by 4, and you'll get that t is equal to 12. So in either case, you would have gotten the right answer. The idea is to wiggle them down to where their primal base, their prime bases, are the same, like we have here. So we had their prime base on this was just a 2, and the prime base on this was actually just a 2 as well. Once you get them written as 2 to a power is equal to 2 to a different power, you can now say those powers must be equal. So this tells me that in 12 days, 51,000 some odd people will know. Just write that in there. That's a pretty short period of time. That's how powers work, though. Very neat. Now, as another application for solving equations, exponential equations, this one I'm going to show you how to use your graphing calculator on. For several days after the Northridge earthquake on January 17, 1994, the area received a number of significant aftershocks. The color graph on this graph over here, the red part of it I should say, shows that the number of aftershocks decreased exponentially over time. And this data is from the LA Times, June 27, 1995. So it does look like it decreases or decays exponentially. And the reason why is because there's this black curve that's an actual exponential decay. So the graph of the function is, well, they use letters I really don't like. You could always change the letters in a problem if you want. They use S of d is equal to S naught a to the d, and then they say it approximates the data. I probably would change that, mainly because I just dislike their lettering, and I will go back to my P of t is equal to P naught b to the t, just because, well, I could do it. I'm allowed to, so are you. So read the value of P naught from the graph. Remember, P naught is the initial value. So it looks to me that initially that's 150. What that means is initially there was on that very same day there was 150 aftershocks. Find an approximation for the decay factor, which is going to be this b value, by comparing 2 points on the graph. Now you can select any 2 points that you want on the black curve, because that's the curve that we're going to use. Although in reality, you use, if you're going to do some real data analysis, nobody comes along and gives you this black curve. You actually have to select points on this red curve. So they're telling you some points on the graph are approximately 1,82. So they're saying like, oh, I see, because this is 1 right here. 1,82. So they're saying that this point right here is about 1,82. And 2,45, so they're saying that this is probably about 45. And in reality, I think they're using the black curve, so they're kind of going in between these, and they're saying that that is 2,45. But like I said, in reality, you would probably use the red curve, or maybe what they're doing here. Maybe you should draw this curve along here and say, well, that looks like a pretty good fit. Let me just estimate in between what some points might be that would fit this data somewhat nicely. And they give you 3,25, which is right about here actually. And finally, they give us 4,14. Well, that's 10. It's actually a little bit higher than 14, but let's just say it's 4,14. Okay, so they give me those 4 points. Now I could use any of those 2 points to determine the decay factor. Or I could use a calculator to actually get a better approximation to the decay factor. But I'll show you both here. Let's use the points 1,82. and 2 comma 45. Now there's a lot of fancy ways you can go about doing this, but the fact is that if your points are right next to each other, if you can set them up in a table like, well, we're using T's and P's, so if you can set them up in a table and it goes 1, 2 for your input values, and 82, 45 for your output values, you can find out what the decay factor is just by noting, well, every time I step by 1 in the inputs, my output should be multiplied by some number I don't know. I don't know what that number is, and I want to find out what that number is. In fact, we're going to call that number B. So it gets multiplied by some base. So let's see. 82 times what number is equal to 45? Well, let's find out. Let's divide both sides by 82. 45 over 82. Let's see if that reduces, which it doesn't. I don't see anything in common here. So this tells me that the base is 45/82. Let me go ahead and go back to the previous page. I see the decay factor is 45/82, so that's what B is. So my actual function that I think is good for this is P of t is equal to 150, because that's the initial number of aftershocks, times 45/82 raised to the t power. Now we could always check this result just by plugging in some values to see some of these points that we said should fit on this curve, to see if they actually do kind of fit on the curve. The way you could do that is bring up a graphing calculator or any type of calculator, and you enter your function in. Here's the basic way most students will do it. I'm just going to show you this first, and then I'll get to the more advanced, better ways. So our function is 150 times parenthesis 45/82 end parenthesis. Oops. And let's see, what time am I going to look for? Let's evaluate this at 3. So I'm going to plug in day 3. And I'm hoping this will return something near to 25. It won't return exactly 25, because the fact is we're kind of just ballparking it here, but we're hoping that it will return near to 25, and it does. It returns very close to 25. So let me try that with day 4, and I'm really hoping that that returns something near to 14. It kind of does. It's a little bit off, but hey, that's okay. When we're talking number of aftershocks and somebody says, you know, you're rounding, that is 25 and 14, really. So that's a pretty good approximation. Not too bad at all. Now, the other thing I want to do here is I want to show you how you can really get some cool results using your graphing calculator. So I clear my screen. Now get ready to learn. Put your learning hats on. I'm going to first hit y equals, and see I'm just going to clear out any of the functions I have in there already. And I'm going to type in the function that I've been given, 150, or the function that I calculated, times the parenthesis 45/82, and raise that to the x power. Okay. And I know it's supposed to be t power, but whatever. If you hit graph, you're not going to see anything, because guess what? It's off your screen. But that's, well, okay, it's not totally off my screen. Actually, you see it right there. But that's not what I'm really concerned with. Well, I suppose I could be concerned with it. Let's adjust our window and say, I'm not really concerned about anything before the 0th day. And I'm going to try to match it up to their graph. I want to go up to the 6th day. And let's see, their graph starts at y equals 0 and has a y maximum of 150. So let's see if my graph kind of looks like theirs. That's not too bad, right? Now, I've shown you some of these tricks before, but there's a lot of tricks you're about to learn, so get prepared. One thing, if you hit trace right now, you can kind of go along this curve to the left and right and find out what x values give you what y values. And once you have hit that trace button, so once you have this x, y business down here, you could type in a number like 1 and hit enter, and it'll tell you, oh, when x is 1, the output's 82.31 blah blah blah, which is close to my 82. And when I type in 2, the output is 45.17, which is close to my 45. And when the output is 3, again, we know that's 24.79. When the output is 4, the output, or when the input's 4, the output is near to 14. So this is a really cool way that you can get all these values. You could also look at them in a table. So if I hit second, notice I have hit the second key, and table menu is right above the graph button, so hit graph, you get a bunch of x values and a bunch of y values. Now yours might be different, so let me set yours up for you. To set the table, you have to go to the table set feature. So hit second window to access the table set. And this just asks you, hey, where do you want the table to start? 0's perfect place. What do you want to increment by? Delta, capital delta there means increment or change in the table value. So I don't mind it changing by values of 1, going t equals 1, t equals 2, t equals 3. But what's important to me, actually, is this business down here. I want it to ask me. I don't want it to automatically create a list. I want it to ask me what I want to plug into my function. And I'll let it automatically figure out what the answer is. So now that I've done this, I'll hit second table again. Notice my table's empty, but I'll plug in 0. And then 1. And then 2. Then 3. See, notice this is giving me the same values, but it's just really clean. Very nice. All right. So you see, like, for example, after 6 days, there were only 4 aftershocks. Always keep in mind the application you're dealing with, because that interpretation for the applications is super important. Now, if you thought that was a lot, it wasn't. Because all I really told you how to do is, well, graph a function, which I've told you how to do in the past, and how to look at a table and build a table of values, which I've told you how to do in the past. And I told you how to use the trace button and to go to an exact point on the graph, which I've told you how to do in the past. So there has to be something new I'm going to teach you, and you're absolutely right. We are now going to make a group of statistics. Not like averages and means and medians, modes and stuff like that, but a list of data. So you see this stat button here? If you're given a real situation where somebody says, hey, here's a bunch of data points, I need some type of function that fits this, then this is the button, the go-to button. You're going to hit stat, and notice all these sub-menus. You have an edit menu, a calculate menu, and a tests menu. But the edit one is what we're going to work with initially. We're just going to edit a list. So just select that first option there. Here's my list menu. I have list 1 and list 2. In list 1, I'll call those my x values. In list 2, I'll call those my y values. So my x values are 0, actually. Sorry, I typed 1, but I meant 0. 0, 1, 2, 3, and 4. In my y values, or my outputs, I had 150. By the way, that was my guesstimate that it was 150. It looked like 150. 82, 45, 25, and 14. Very important that those two lists be of the same length. Now, really, right now, there's nothing that I can really say. It's not going to do anything for me just to have this list in here. But let me quit out of this menu. So second quit. Back to the main screen, the home screen. And I'm going to go back to my y equals here. My function's right here. See this little top menu? It says plot 1, plot 2, plot 3. That's where you can turn on your plots. And I want to plot these points. So what I'm going to do, you could either go up here and just hit enter, or you can exercise a little more control and hit second and hit y equals. When you hit second and y equals, it accesses the stat plot menu, because we're going to plot a bunch of points. Let's use this. Now, I'm going to just use this. If you're only going to, it's like the function menu, this y equals thing. There's no point in starting writing an equation in y4 if you haven't filled up y1, 2, and 3 yet. So same thing in this menu. There's no reason to use plots 2, 3, or whatever if you haven't used plots 1 yet. So let's use plots 1 here. Let's click enter. I'm going to turn it on. It's automatically set for a scatter plot. In other words, it's going to plot points. And it should automatically want your X list to come from that list 1 and your Y list to come from that list 2. If it doesn't, down here on your keyboard, you see the number 1 Right above it is an L1. You would hit second L1. Okay? Same thing for L2. You do second L2 if you needed to. And then you could just go ahead and hit graph. And look, it has my points on there. Look how nice that fits too. Very, very nice curve. If you have a hard time graphing or getting the right size window, if you have data points already, you can actually hit zoom, and if you scroll down quite a bit, the ninth option is to zoom to your statistics. If you hit that, it'll zoom to a window that exactly fits your data points. You can see in this window, now I've zoomed in a little bit, I noticed that at x equals 3, it's not the perfect fit. So is this all you can do? And the answer is no. Let's recap really briefly what I've told you to do. Graph a function. You already know how to do that. Just type something in, hit graph, and there it is. I've told you how to adjust a window, but we know how to adjust a window. I've told you how to zoom on things. I've told you how to trace along your graph. Okay? But now, oh, and I also told you how to enter in a list of data through the stat button. You hit stat, edit, and then you can enter in your list of data. And then to plot that data, you would just go to stat plot. So second stat plot here, and you could turn those on. So this is all I've told you to do. It still seems like quite a bit. Now, if you are not faint of heart, let's try one last thing. And this last thing is probably the coolest anyway. What I'm going to do is I'm going to go ahead and delete our function here. So it's no longer there. If I hit graph, you'll see all I have are points. Now what I'm going to do is second quit and go to the stat menu again. Remember, I already have a list 1 and list 2 with my x and y values. Now I'm going to calculate, hop over here, I'm going to calculate a regression curve. And this will be, what a calculator does is it gets you the best possible curve that will fit to this data. And you get to actually select what type of curve it is. So you could select a line, try to fit a line to all 4 of these points, which is not going to happen. You try a quadratic function, or a cubic function, or a quartic function. But I'm actually going to do an exponential function because we're talking about exponential function. So I'm going to go ahead and select that. So again, it's under your stat menu. You select calculate because you want to calculate a regression curve, and select exponential regression, or XReg. Hit enter, and it doesn't look like anything happens. The reason why is it's expecting you to tell it where your x values are stored and where your y values are stored. As long as you stored them in list 1 and 2, it automatically assumes that's where you want. So if you hit enter again, it'll give you the perfect regression equation. If you didn't store in list 1 and 2, if you stored in list 3 and 5 or something like that, then you could label them here. You could say second list 3, comma, second list 5. But in my case, I did list 1 and 2, so let me go ahead and delete these out of here and just hit enter. Because like I said, if there's nothing entered, it'll automatically assume list 1 and 2. So here's where it says the perfect function is 148.8 for the coefficient, or the initial value, and 0.5526 for our base. I wonder how close that is to this. I can't remember what this was. So the base that we had calculated was 0.54878. That's very close. But let's go ahead and use the function, the exponential regression function. Remember the P naught for that the calculator got was 148.8, and the base is 0.5526. Now, do you want to type in all those things? Probably not. You could if you want to. You totally could. You could go to y equals and you could type those points in, or those values in. But I will show you a better method First thing you do is, and it doesn't matter if you clear your screen or not, I just like to clear my screen. First thing you do is you want to, up here, hit y equals, so you're in the function menu, the graphing function menu, and you're going to insert a variable here. So I'm going to go to the vars button. It's the only time you're likely to use this. So just watch, it's pretty neat. You know the vars, and there's a lot of weird things going on here, but I just did something with the statistics. I know I did something with the stat menu. So let me go to that thing. That might be a good thing. So vars and then stats. And man, there's just too many choices. I'm overwhelmed. Oh, but wait a second. I just made an equation. There's an EQ right there. Maybe I should go over there. Oh, look at that. Reg EQ. If I hit enter, it will automatically insert the regression equation that I just calculated. So again, the keystrokes are, let me clear this line out so you can see it again. Although you could rewind, so I don't know why I'm saying that. You get to this y equals menu, hit vars for the variable. We're working with some set of statistics, so select that, and you want to insert an equation, specifically the regression equation. Now if you hit graph, this curve is the perfect curve to this data. And then you can make predictions and use this function for other things, predict how many quakes 10 days from now, that type of thing. Pretty neat. And that'll about do it for solving exponential equations without logs.